Then these are known as the memory access attributes. So what do you mean by memory access attributes? To certain memory locations, there are certain attributes associated with it. Say for example, bufferable. Say when do we tell that a particular location is bufferable? Write to memory can be carried out by using a write buffer. Right. Even though the processor is continuing with the next instruction execute. Right. The processor will be busy in executing the next instruction, but even at that time, you can write it into a write buffer. Right. So write process will not be disturbed. That is so. If you are having that capability for that location, that is known as, or to that memory, that is known as bufferable memory location. So when do you tell a memory is cacheable? There will be a cache associated with the memory. So whatever data you are read from the memory will be placed in the cache, right? So that whenever you want to read this data, you can directly read it from the cache. So what is the speciality of using cache? Your reading process will be more fast. Instead of accessing from the memory location, you are accessing from the RAM, from the cache. Then when do you call a memory is having executable memory attribute? When do you call that? If a memory is capable of storing, for example, a program code which can be executed. Right? So if you are having a memory which is capable of storing a program which can be executable, right? Then such kind of memory location is known as having executable memory attribute. So if you want to store the program, you should store it in a memory which is having executable access attribute, right? Then last one is shareable attribute. So if you are having a memory with access attribute shareable, what does it mean? The data stored in that memory area can be shared between multiple masters. That means you can share that data across different type of buses at the same time. That is known as shareable memory attribute, right? So in Cortex, each memory region will be having one or more memory access attributes. One or more. Some of the memory location will be having only one attribute. Some of the memory location will be having more attributes. These are some of the advantages of using the bit banding. Bit band operation can be used to simplify branch decisions. If you are checking a particular bit and you need to perform a band, if that bit is set, say it is something like, let us take you are having an ADC interrupt flag. Whenever ADC is generating an interrupt, you are setting a flag. For example, flag means it is a bit present in one of the register. Right. And if that bit is set, you need to perform one task. If that bit is clear, you need to perform some other task. That is my aim. So normally what you will do, you need to read that whole register. You need to mask all the unwanted bits. You need to make it to 0 by handing with 0. Right. Then finally you need to compare the bit. If it is 1, you need to go somewhere. If it is 0, you need to go to some other memory location. But if you are using bitband region, what is the advantage? You can directly read from that bit using bitband alias region. Then based on the value, perform the branching. So you can reduce the branch decision time using bitband region, because you don't need to read it, mask it, and again compare. You can directly read, compare, and do the operation.
So let us consider the second advantage of bit banding operation. That is, bit banding is essential for situations in which resources are being shared by more than one processor. Right. So let us consider an example here. Let us consider that this is a time axis and this is a main program, and this shows the value present in the output port. So in the main program, the value from the output port, that is 0x00, is read to a register, that is 0x00 is read to a register. Then bit 0 of this value is set by the main program. Then it is written back to the output port. So when the 0th bit of 0x00 is set, what will be the value? 0x01. So 0x01 is written to the output port. After some time, this value, that is 0x01, is read to a register, right? And again bit 0 was cleared by the main program, right? So 0x01 was read to a register, then bit 0 is cleared. When bit 0 is cleared, what will be the actual value? 0x00, right? So now bit 0 was cleared, but it has not been written back to the output port. Before writing it back to the output port, that write process has been interrupted and an interrupt handler came into picture, right? So in the interrupt handler, the same value, that is 0x01, was read to a register. Then bit 1 was modified, that is bit 1 was modified, or it has been set, right? So previous value was 0x01. Now in the interrupt handler, bit 1 is also set. So what will be the actual value? 0x03, right? So that 0x03 is written to the port, output port, right? So once the interrupt handler execution is over, the previous main program will get resumed. Previously what was done in the main program? Bit 0 was cleared, right? And once the 0 has been cleared, bit 0 has been cleared, the value will be 0, 0. But that value was not written back to the output port. Before doing that, interrupt handler has interrupted the operation and it has set to bit 1. So instead of getting the value 0x00, 0x03 was written on the port. But once the interrupt is over, the remaining portion of the main program, that is writing the value back to output port, was executed. What is the value written? The 0th bit of 0x01 was cleared. So the value that is to be written will be 0x00, right? So once the interrupt is over, the main program resumed and 0x00 was written onto the port. So what was the problem here? Whatever change that was made by the interrupt handler was lost. Why? Because interrupt handler has set first bit, right? And that first bit has been set means it will be 0x02. If the previous value was written here itself, what will happen? When you are clearing the 0th bit, you will be getting 0x00. Then in that 0x00, if you are setting first bit as 1, you will get 0x02, right? So finally we should get 0x02 if the main program and the interrupt was executed properly. So instead of getting 0x02, now we are getting 0x00. So what does it mean? The change that was made by the interrupt handler was lost. Why it was lost? Because the read, modify, write operation has taken place. Right? Read, modify, write operation was taken place, and before the write operation has completed, read and modify has been done, but write operation was not completed. Before completing that operation, interrupt handler got executed, right? So the change made by the interrupt handler was lost. So this is one of the disadvantage of using the non-atomic read, modify, write. Why this process? Why this problem arise? Because the same resource, the same data present in the output port was shared by the main program and the interrupt handler, right? And since bit banding was not present here, the read, modify, write that was not atomic in nature, so that it was interrupted in between. Then here with the bit banding operation, if you are doing the same task that you have seen just now, how it will be done? In the output port you are having 0x00, right? And at this point, bit 0 of the value present in output port will be set by the main program. How it is being set? By using logged read write modify. That means by writing to the bit band alias region. In the previous case, the value was read from the port, bit 0 was read, then it was written back. So here the read, modify and write was not atomic in nature. But here, instead of doing that, the bit 0 was set by the main program by writing to the bit band alias. Instead of read, modify and write, directly that value present in the bit band alias region is set as 1 by using read, modify, write. That is logged read, modify, write. Then so the value will be 0x01. Then after some time, at this point of time, again what has to be done? We need to read from the output port, right? We need to read from the output port. Bit 0 should be cleared, right? Here bit 0 was set. At this point we are trying to clear the port, clear the bit 0. So that also is done using logged read, modify, write. Right. So instead of reading the 0x01, clearing the 0th bit and writing it back, instead of that, directly 0 has been written onto the corresponding bit band alias. We will get 0x00. Then similarly in the interrupt handler, what it was done previously, bit 1 was written. Right. So instead of read, modify and write, bit 1 was modified by the interrupt handler by setting that corresponding bit in the bit band alias. So again logged read, modify, write was done. Right. So when you are setting the first bit of 0x00, you will get 0x02. So previously, since the read, modify, write operation was interrupted by the interrupt handler, you are getting a wrong value as 0x00 instead of getting 0x02. Right? But now by using bit band operation, we are able to get the correct value as 0x02. So this is a second advantage of using bit band alias whenever a data is shared between two different processes.
So similarly, when if the memory is shared between different tasks also, the same thing will happen, can happen. Right? It can be interrupted in between if we are not using bit banding. But with the bit banding, again the same atomic operation will be performed. So even though it is shared between two tasks, or even though it is shared between other things, the bit banding will be useful in protecting the data. The next advantage is bit banding feature. It can be used for storing and handling Boolean data. Storing and handling Boolean data. So it is almost the same functionality. The whatever Boolean variables you are having in your program, that can be packed into one single memory location. So if you are having 32 Boolean flags, for example, all these 32 Boolean flags can be packed onto a single memory location. Right. Otherwise, you need to define it separately and it will be in separate location. But here you can pack all the Boolean data. Maximum Boolean data can be packed onto a single 33 memory location, 33-bit memory location. But whenever you are accessing it, you can access it as a separate bit using the bit band alias. Right. But for storing process, you can use a single memory location. Then the same bit banding, it can be used for serial data transfer. How it is performing serial data transfer? The same method. Instead of sending the data one by one and shifting it, you can directly read from one address and send the data. Again read from the next address, send the data. Right. So this process is known as bit banging. So it refers to driving IO pins under software control for serial communication. Right. So if you want to send some serial data, which is some critical for some critical operation, you can use this bit band method for performing bit banging operation. Because no need of shifting or any other additional operations are not required. Directly you can access the bit band alias, you can send it to the serial pins. So this bit banding operation is not limited to word transfer. You can see here, if the data is starting from this location, next data will be here in the third byte, next data will be here, next data will be here. If you are starting your access location from here, again the same thing will be there. So bit banding operation can be used for unaligned data transfer also. Aligned data transfer means always your first byte will be in 0th location, this location, 4th byte will be in this location. Always it will be like that. But here bit banding can be used for unaligned data transfer also, whether it is word aligned or half word. Right. These three are in the case of word aligned. These two are in the case of half word. So irrespective of the alignment, you can use the bit band. Then this is a pipeline feature available in Cortex M3. So what is the use of pipeline? So if you are not having pipeline, what you will be doing means first instruction will be fetched, decoded, executed. So let us take each stage will take one instruction cycle, for example. So for executing one instruction, it will take at least 3 cycles. If you are having three stages in execution, right? But if you are having pipeline incorporated in your architecture, what will happen? It is something like a pipeline. So what do you mean by pipeline? First instruction will be in the fetch stage, second instruction will be in the decode stage, next instruction will be in the execute stage. So all the stages will be having, or in each instruction cycle there will be multiple stages. Say in this instruction cycle you will be having two stages or three stages. In this instruction cycle again 3 stages, like that. So in each instruction cycle, more than one operations will be performed. Right? In this instruction cycle, one instruction will be fetched, previous instruction will be decoded, the instruction previous to that will be in execute. So generally, each instruction cycle will be having 3 stages. So what will be the execution time? The total execution time will be, if you are taking average, the execution time for the instruction will be almost divided by 3. If you are taking on an average, each instruction cycle will be executed in a one cycle divided by 3, right? Because more operations are done in each instruction cycle, right? Total execution time divided by 3. That means that means you can infer that most of the instructions will be executed in a single cycle. Previously 3 cycles were required, but since you are having 3-stage pipeline, you are dividing that instruction cycle time by 3, so you will be getting 1 cycle per execution of one instruction on an average. And in the case of pipeline of Cortex M3, you are having one more feature known as instruction buffering. Instruction buffer. So what do you mean by that? So if you are seeing this example, let us take these two. Instruction D and C2 will be in fetch stage, right? And C1 will be in this instruction buffer. C1 will be in instruction buffer. C2 and D will be in fetch stage. Then the next two will be in decode stage. Next two will be in the execute stage. Right. So instruction buffer Actually, it is behaving something like as a, you can equate it some cache memory, for example. Not it is not a cache, so you can consider it something like that. So it can be accessed more in a faster manner, right? So instruction C2 and D will be in fetch stage, B will be in decode, A will be in the execute stage, and C1 will be in the instruction buffer. So that in the next cycle, C1 will be taken into the fetch stage. Right. So by adding instruction buffer, you are increasing the speed of execution time by some units. But actually, when you are executing a program and when you are writing a program, you will not be aware of all these things. It will be done all in the background. Right. When you are writing the assembly program also, you will not identify that these operations are carried out, but it will be done in the background. Then this is a detailed block diagram of Cortex M3. Right. So you are having Cortex M3 core here. Two buses are there. Instruction bus, data bus, and one more bus is there. It is coming from the debug interface. What is this SWJ and DP? SWJ-DP and SWJ-DP. I have told the
Serial
name.
wire debug port.
SWJ means what? Yes. So two types of debug ports are there. One is serial wire debug port. Another one is serial wire and JTAG debug port. So it is used for connecting the debug interface. It will be connected to the AHB access point through something known as debug access port. So debug access port is controlling this, right? So there is one debug access point, instruction bus, and data bus. All the three are connected to something known as bus matrix or bus interconnect. So bus interconnect again, it is subdivided. These three buses are subdivided into four categories. One is known as I code instruction bus. Another one is D code, that is data bus. Another one is system bus and private peripheral bus. Right. These are the different types of buses available in Cortex M3. Whatever data it is sent through this bus, it is aggregated or collected here in the bus matrix and supplied to the corresponding buses. Right. Then here the memory protection unit is optional in the case of Cortex M3. So it depends upon which controller you are using. Which controller you are using depends upon that. So it is an optional. The debug components here, these are the debug components. Some of them we have seen before, right? So this is data, watch point and trace, instrumentation trace macro cell, etc. Then embedded trace macro cell. So this embedded trace macro cell, it is used for tracing what? Tracing the instruction. Right. So it is given to the trace port interface unit to the trace output. So trace port interface unit is used for collecting all the trace information. It is used for collecting all the trace information. Right. Then these private peripherals, you can see internal private peripheral bus is connected to ITM, DWDT and NVIC. Internal private peripheral bus is connected to the ROM table, TPIU and ETM. Right. So there are internal private peripheral bus and the external private peripheral bus. Then NVIC we have seen. Then what do you mean by system tick? I think we have, I don't know whether it is covered before. System tick means what? What does it mean? So it is a particular timer. It is available along with NVIC. So what does it do means, for example, I have told that when I have taken interrupt, I have told that whenever interrupt is generated, the processor will detect that interrupt and it will execute the ISR. Right. And this process will be monitored by VIC. In this case, NVIC. So at what time NVIC will scan for the interrupt? That is done based on the system tick timer. So in the system tick timer, it is used for defining the time, or it is a tick timer, which is a basic unit of timer for the interrupt. You can call like that. Right. So whenever system tick timer is counting 1, NVIC will check whether an interrupt is there or not. Right. So if interrupt is there, then it will do the necessary actions. And here one more block is there. It is known as WIC. What do you mean by the WIC? Idea? Both non-maskable interrupt and other interrupts, all are connected to WIC. If it is configured, WIC will give some information to this NVIC. So what does this WIC means? So WIC is known as wake up interrupt controller. Right. That means, for example, you have configured this Cortex M3 core to sleep mode or deep sleep mode. So when should the processor come out of the sleep mode or deep sleep mode? Basically it should come out of the sleep mode or deep sleep mode. When it should come? At least whenever an interrupt is generated. Whenever an interrupt generated, the interrupt is generated, it should come out of that. So if we are configuring the wake up interrupt controller, whenever an interrupt is generated, NVIC will tell, the VIC will tell NVIC to wake the Cortex M3 core so that it can execute the ISR. Right. So wake up interrupt controller, from the name itself you will get some idea. It is used for waking up the processor from the sleep mode when an interrupt is generated. That is known as wake up interrupt controller. If it is not configured, then it will be working as a normal manner. If it is configured, it can take the processor out of the sleep mode or deep sleep mode. Then all the peripherals brief introduction I think we have given. So these are the expansions of all these things, what I have told now. Then go through that. And these are the code, system bus, external private peripheral bus, and data access port bus. Right. So what is the use of iCode bus? It is used for instruction fetch. From where to where? From this location to this location. What is this location known as? Code memory bus, code memory. So iCode is used for fetching instruction from code memory. Then what is the use of decode? It is used for accessing data from this location. Which is this location? The same location, code memory. Right. So the instruction and data which is stored in code memory can be accessed by these two buses. Then system bus. System bus is used for instruction fetch and data access from these two separate locations. Which are those two locations? From here to here and this location. So system bus is used for accessing both instruction and data from this location to this location, that is including SRAM, peripherals, external RAM and external device, and the vendor specific information. These are accessed using. Right. So why it is known as instruction fetch and data fetch? Why it is known as instruction fetch? Because here instruction is not there, no? But why they are telling instruction fetch also? I told instruction will be written in code memory area. Data can also be written here. So instruction and data will be fetched from here. But in system bus also instruction is fetched. That is how it is written. But how the instruction is fetched here? When I was talking about memory attribute, instructions can be stored in code memory, SRAM and external RAM.
if you want to execute data and code parallelly, we need to store it in code memory.
Otherwise, you can write the instruction in SRAM as well as in external RAM. So that is why system bus is said to be, it is used for accessing instruction from these two locations and the data from other locations. Finally, you are having external private peripheral bus that is used for accessing this memory location and some part already used by this location. You can see here. So external private peripheral bus is used for accessing this part. Internal private peripheral bus is used for accessing this part, this location. What are these contents? These are the contents accessed by instruction, or these are the peripherals that can be accessed using internal private peripheral bus. External private peripheral bus are used to access these components. Generally, private peripheral bus is used for interfacing debug components. Right. And these are the protocols are also shown here. AHB Lite, APB bus. And finally, you are having debug access port. What is a debug access port? It is used for interfacing this to the debug hardware. Then, in addition to the signals which I have told before, these are some of other interfaces. Right. First one is multiprocessor communication. It is used for task synchronization between different processors. If you are having multiple process, you will be using these pins, these lines. Then sleep signals are there, which shows the status of sleep operation. Then interrupt status signals are there. It shows status of interrupt operation of ETM and the debug peripherals. Right. Then reset request signal is there. It is a reset from NVIC. Then other lockup signals are there. So these are you need to only go through it. You need to just understand because these are not so important. But you need to identify that these are some of the other interfaces which is connected to your Cortex M3. Some additional functionalities are given by this. Then these are the types of reset signals available in Cortex M3. First one is power on reset. All of you know that. What do you mean by power on reset? Whenever you are resetting the processor, power on reset will happen. Right. So it will reset the processor core, peripherals, and the debug system. Right. So the complete thing will be resetted, including the processor core and peripherals. Processor core, peripherals, debugging system, whatever it is there, it will be all the blocks will be resetted in power on reset. Next one is system reset. So the system reset, it will reset the whole system, including the processor clock, processor core, NVIC, MPU, peripherals, but not the debug system. Right. So in system reset, debug system will not be resetted. Other blocks will get resetted. So if you are generating system reset, other blocks including processor core and peripherals will be resetted, but debug system will remain unresetted. Right. Then next type of reset is processor resets. So from the name itself you will get the idea. It will reset the processor core. Right. So it will affect the processor system including the processor core. But again, the debug system will not be resetted. And the peripherals also will not be resetted. Only the processor core will be resetted. Right. Then last one is JTAG reset. It is used for the debugging purpose. Whenever JTAG or whenever debug peripheral is asking for some information, you can give JTAG reset. It is used by for the debugging operation. And this will be done only if you are having that JTAG debug access port. I have told SWJ debug access port and SW debug access port. If the controller is having SWJ debug access port, then only debug access JTAG reset can be generated. Otherwise, this JTAG will not be there. Only single wire reset, single wire debug access port will be there. Right. So this again depends upon the manufacturer of the controller, whether JTAG reset is there or not. So this is a block diagram. External reset signal connected to reset generator. This reset generator will be generating the corresponding reset, system reset or power on resets. Right. So power on reset will reset the processor core, debug system, and debug interface. All these things will be resetted. But in system reset, only the processor core and the peripherals will be resetted except the debug interface. And JTAG reset will be given to the JTAG in a debug interface. Then some more details regarding the exception type. So small introduction I think we have given before. 1 to 15 system exceptions are there. Right? And from 16 to 239 you are having external interrupts, but again it depends upon the manufacturer, right? And the value of the current executing interrupt will be available where is it available? Current execution interrupt number, where it will be available? Any idea? So it is present in a status register known as IPSR. It is here itself, IPSR. What do you mean by IPSR? There were 3 status registers, no? Application program status register is containing all the what is that, flags. Then interrupt program status register, it contains the number of currently executing interrupt or exception. Then one more status register was there, no? What was that?
Execution program
Execution
status.
program status register. It shows the status of certain special instructions known as if then else and continuable interrupt continuable instruction that we will see later, and the thumb state is also present there. So the currently execution interrupt number is available in IPSR, interrupt program status register, right? And let us take your exception has been enabled, and if one exception is generated, but at that time some other high priority ISR is executing. So what will happen? So there is a special signal for that, interrupt pending status signal. So your current instruction will be kept in the pending state until the first instruction was executed. Right. Why the first instruction was executing? Because it is having high priority. Right. So if the next priority interrupt is coming, it will be kept in pending states. Unless some of the exceptional fault conditions are occurring, like non-maskable interrupt, reset, etc. So other than those interrupts, all the other things will be kept in the pending state, pended states. Right. So pending status bit is there, and this is used instead of FIQ in the normal ARM7 process. Right. This pending feature in NVIC is used as same as FIQ signal, FIQ fast interrupt request in the other traditional controllers. So what is the advantage of that? Why that pending feature is there? It is written here because sometimes the interrupt may have generated here. At that time it will be kept in pending state, and after some time the previous interrupt was executed, then this pending interrupt will be executed even though the interrupt source has deasserted it. What does it mean? Now it is not generated, it is not having that interrupt. Previously it has generated that interrupt, but now it is not there. So even though the interrupt is not there presently, it will be executed. Why? Due to this pending status bit or pending signal, the pending feature. That is the advantage of pending status bit or interrupt pending feature. So this is what we have seen before, 0 to 15. These are the interrupts or exceptions available in Cortex M3. All these are different kind of exceptions. Some of the exceptions such as usage fault, bus fault, memory management fault, and hard fault we'll see in detail later. These are the 4 bus faults, or these are the 4 exception or fault conditions which are very important. So memory management fault or hard fault will be generated when corresponding fault handler is not there. Memory management fault will be generated if MPU violation is happening. You are trying to access a memory location which is logged by MPU. Or if you are trying to access some location which are not available. Then bus fault will be occurring whenever there is an error, that is data abort or data prefetch abort. Usage fault will be generated when you are trying to access some coprocessor instructions, and some other features are also there. Right. So these are the 4 fault conditions. Others are the exceptions. Then these are the interrupt exception numbers from 16 to 255. These are the exception interrupt numbers. These many external interrupts can be possible, but again it depends upon the manufacturer. They'll be giving only 16 or 8 or something like that. Depends on the manufacturer.